Okay, here we go with galaxies. This is a fun topic, so get ready for fun. All right, element of the day is iron. There's a whole industry built around iron in the United States, and that industry has been faltering of late. And part of the reason it's faltering is that our iron industry is not modernized. Uh, Iron production in Europe and in Japan is much better because Europe and Japan were bombed like crazy during World War II. And so all of their iron producing facilities are dating from at least the end of World War II. The United States iron producing facilities are usually quite a bit older than World War II. Iron itself, not particularly useful to humans. It has to be mixed with carbon to make steel. If you don't mix iron and steel, even bronze is stronger. This is why the Bronze Age came before the Iron Age. From an astronomer's perspective, the most interesting thing about iron is that it's the most stable element in the universe. So if you can recall, or stretch your mind back, what causes a high mass star to go supernova? It happens when the core is iron, because iron will neither release energy when it absorbs other atoms, nor will it release energy when split apart into other atoms. Anything smaller than iron by atomic number, by number of protons in the core, will release energy when it's combined together to form another atom. Any element that has more protons in the core than iron will release energy when it is broken apart into other atoms. And that's the difference between fusion and fission. Iron itself, it's the top of this binding energy curve. You get energy when you go from lower to higher in this graph. Since iron's at the top, there's nothing you can really do to it to get energy. Glom on other atoms, you have to put extra energy into iron to make it accept them. Try to break iron apart, you've got to put extra energy into iron to make it come apart. This is why the universe is slowly filling up with iron. Don't get me wrong, I'm not saying eventually there'll be more iron than hydrogen. I'm just saying that once iron is created, it's pretty much always there from that point on, unless it's blown apart by a fantastic explosion, or turns into a neutron star, which often happens, or is sucked up into a new black hole, which we'll deal with in relativity, and that often happens as well. So today we're going to talk about galaxies, and in particular a little bit about our own galaxy, which is creatively called the Milky Way. And we're going to talk about how we figure out how far away galaxies are, which is a method that uses something called standard candles. We've already talked about the most important standard candle, which is called a type 1a supernova. Type 1a supernovas happen when a white dwarf star absorbs so much matter from something else, almost always a companion star, that the mass of the white dwarf star exceeds 1.4 times the mass of the sun. When this happens, the whole white dwarf star spontaneously explodes. Almost all the matter is transformed directly into energy. It's super bright, and we think that when this occurs, they're all about equally bright. So every time we see one, they're very obvious because they are so bright. And if it is true that they're all equally bright, the moment we see one, if it's true that they're all equally luminous, which is the measure of how much light is put out, then all we have to do on Earth is measure how bright they are, how much light from them is actually entering our telescope. And then boom, we instantly know how far away the galaxy that's hosting the white dwarf star is. Because we know that light itself gets weaker by area. It gets weaker by a factor of distance squared as you go away from the source. The Milky Way galaxy is the one we live in, and we can see it partially. Go out to very dark night skies and you can observe a brightish glow that goes across the sky during the summertime in the northern hemisphere and during the wintertime in the southern hemisphere. Because the North Star is currently Polaris, because the Earth precesses, currently the best place to see the Milky Way is in the southern hemisphere. As the Earth continues to precess, eventually the best place will be the northern hemisphere, but certainly not within our lifetime. The Milky Way is not equally bright in all directions because there's a bunch of dust out there, and dust absorbs visible light very effectively. If we had a good infrared telescope out in orbit, we could see through all that dust and we could see the structure of the Milky Way much more effectively, but we don't, so it's a bit of a moot point. Here is a really good picture of the Milky Way, somewhere out in the distance, and we can only see it during certain times of the year because we're out by the very edge of it. For much of the year, the Milky Way is completely washed out by the light from the sun. It's still out there. We just happen to be on the far side of the sun from it, and so there's no seeing it. But when we travel halfway around the sun, and we are a bit closer to the center of the Milky Way than we were before, and the sun's not washing it out, then that's when it shows up and when it can be visible to us. The center of the Milky Way is more or less in a constellation called Sagittarius. Well, it's completely within a constellation called Sagittarius, but it's not dead on in the middle of it. So that is where you would look for it if you were searching for the central black hole in the Milky Way called Sagittarius A. Not every galaxy has a big old black hole in the middle of it, but ours definitely does, and so do most of them. So here's another whole sky picture of the Milky Way, which is why the perspective is all distorted. And right in the middle of it is Sagittarius, and our galaxy happens to have a big old circular bulge in the middle of it, and that's one of the gives that it says that there is a black hole there in the center. And again, it would look like a huge spherical bulge in the middle with bright arms extending out to either side, were there not a lot of dust in the Milky Way. Of course, were there not a lot of dust in the Milky Way, then planets like Earth and Mars and Venus and Mercury wouldn't exist. It would be all gas giants from one end to another, because dust also implies the presence of heavier elements. So, often in astronomy, often in many sciences, there's competing astronomers that have such strong views that you pretty much have to wait for them to die in order to arrive at something that's close to the truth. William Herschel produced a map of the galaxy looking at stars that were visible, and he counted the stars in all directions. He assumed that all the stars had the same luminosity, which is wrong. M-type stars are very dim, O-type stars are very bright, and he used that to deduce how far away they are. He assumed that the space between stars is empty, which is more or less true, and he assumed that he could see all of the stars in the Milky Way, which is definitely not true. But with all those assumptions put together, then you can assume that the Earth seems to be the center of the Milky Way, which astronomers keep on trying to put Earth at the center as much as they possibly can. First, Earth was the center of the solar system. Now they're assuming that Earth is the center of the Milky Way. Not true, but what you gonna do? So I'm gonna start video and stop sharing so the video is big, just so I can go over Herschel's assumptions again for you in more detail. So here he is sitting on Earth. He's not making any assumptions about anything really besides that all stars are equally bright and that he can see all the stars in the Milky Way. He counts them all up and he gets something that looks kind of like this, with the exception that there's a big missing bit here. With that missing bit being, of course, all of the big clouds of dust that are preventing our view of stars. Now, just to remind you, this is not what's right. What's actually right is that the center of the Milky Way is somewhere off here. And it goes down to, actually, I need the center to be much bigger than this even, in order for this to be accurate. And it goes down into a bunch of spiral arms, and we happen to be in one of the spiral arms. The perspective here is completely messed up, but hopefully that gives you an insight as to the way in which his picture of the universe ended up being eventually wrong. So there's Herschel's guess. And there would be where the Earth is in his guess. So what kind of data was accessible to them right now? Well, one big clue as to what is out there was the Messier catalog. Back to the board. There's a whole category of things out there called Messier objects. If I were allowed to take a telescope and meet you guys and point the telescope at things, I would at least try to image one Messier object. And here's what you see when you look at it. In just a telescope with just the human eye, they appear to be a blurry mess. If you use a photographic plate, then more detail emerges. Some of them look like that. Some of them look like that. Some of them look like this. Some of them look like this. Who knows what any of these things are? With the naked eye, they're blurry bits with photographic plates to absorb a lot of light for a lot of time. More detail becomes visible, but nobody has any idea at this time what these things actually are. Uh-oh. Hold on. Let me see if I can get the right thing. All right. So there's a Messier object, which to our modern eye appears to be clearly a galaxy. And that's what the galaxy looks like using modern astronomy techniques and charge-coupled devices, which is what eventually replaced the photographic plate and is basically the same technology that's in the camera in your cell phone. So thank you, astronomers, for selfies. And here's another Messier object. What's that? Well, from a modern eye, it sure looks like a nebula. But to the astronomers working at this time, they had no idea that what a galaxy was versus a nebula. There are astronomers alive right now who were present at a time when the existence of other galaxies was somewhat in dispute. I mean, don't get me wrong, they were largely accepted by almost everybody, but not by everybody. So if you use these links, you can get a bunch of the original images and all the Messier objects that were observed. I'm not going to go through and show you all those pretty pictures, but I encourage you to go look through them on your own at leisure. So here's a Herschel's. Quick bit of gossip about them. His sister Carolyn was extremely involved in his research. Remember, astronomy has been always a field of science in which women have been intensely involved and have made many discoveries and have largely not received credit for them. Just like geology, just like physics, just like every field of science, women have been involved in them pretty much from the get-go, and their accomplishments have pretty much been ignored, including up to the current day. Caroline Herschel is one of those people. She was shown here polishing a lens, but she was equally involved in the research that was done. And we've talked about how refracting telescopes are limited in comparison to reflecting telescopes. And a big reason for the limitation is that the lens that goes at the end of a refracting telescope is super heavy. Whereas if you have a reflecting telescope, you can just put a thin layer on the back of the telescope and you've got yourself a mirror, and it can be as light as you can make the mirror thin. But at this time, they were using refracting telescopes, which means there's a whole bunch of counterweights. Carolyn got stuck by one of the counterweights, and it went through, I believe, her arm and lifted her up into the air, and she was almost killed. Nonetheless, she went back to astronomy. I suspect that had happened to me, I might be a little bit soured on the whole business. So this is why early astronomers thought the universe that we live in was only the Milky Way, and it was only centered on the sun, because they were counting stars. And they were counting only the stars immediately around them. So that red circle indicates about what they were able to see. Now, this is a different way of determining where the center of the solar system is. I'm going to go back to the board. There are these things floating around every galaxy. They're called globular clusters. So globular clusters are basically this huge super red, because all the blue stars have been dead for a very long time, pretty much all spherical bodies of very old stars. They used to contain young stars, but they're dead. They appear to have no central black hole. They have black holes within them because there used to be hot blue stars that when they die creates black holes, but they don't have any supermassive central black hole, and they are extremely old. As a matter of fact, one of the problems with calculating the age of the universe is that as astronomers have attempted to do this over the years, they have discovered that often, all right, this appears blurry. I'm going to disconnect and reconnect. Test, test, test. Great. So as astronomers have gone through and tried to calculate the age of the universe, the calculations that they've done often indicate that the universe is younger than globular clusters. So they're that old. They're one of the very oldest groupings of stars. For whatever reason, they've all congealed into these spheres, and the spheres have mainly been attracted to galaxies and held by them. Bigger the galaxy, more globular clusters it holds. The globular clusters are in orbit around the galaxies, almost always. Now, I'm not saying that galaxies don't occasionally capture globular clusters and rip them to pieces and incorporate them. Almost certainly that happens on the regular. But the ones that we see are in orbit. So Howard Shapley comes around, and he has a different take on how to calculate how big the galaxy is. And this is his take. It is very difficult to see things inside of the galaxy. But when you look above and below the galaxy, it's pretty easy because there's no dust in that direction. We're in a very thin part of the galaxy. We're in a spiral arm. And so the globular clusters, being largely above and below the galaxy, are pretty easy to observe. And they're quite distinctive because they're made out of such old stars. You just look at them and you think to yourself, oh, those are extremely red. There should be about 75 of them. And what he said is that these things are orbiting. Oh, okay, completely lost focus again. I'll be right back. Test, test, test. Okay, so assuming that these things are all trapped in orbit, we know that things orbit around more or less the center of mass of a system. So that would mean, given where we see the globular clusters as being, that the center is here. And by the method of star counting, the Earth, the Sun, the solar system, the Earth, Sol, which is the name of the Sun, and the solar system would all be towards the center of the galaxy / the universe, since they didn't actually know about other galaxies. And by this method of counting, we're out towards the periphery, and we just can't see most of it. So, back to the presentation. There's a picture of a globular cluster. I wish it looked more reddish because all the blue stars in a globular cluster are dead. Dead, 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 a long time dead. So, two different ways of looking at it. By counting stars, the sun is at the center of the universe, and we can see stars going out in all directions. By counting globular clusters, the sun is far from the center of the universe / galaxy, because again, the idea of a galaxy was not yet well understood. And there's another diagram of where the globular clusters are and where the sun is. And so the globular clusters are kind of orbiting around an object behind the constellation Sagittarius, which is why we call our central black hole Sagittarius A, because astronomers are not creative about naming things. So the argument is that it is the globular clusters that trace the structure of our galaxy. And the fact that the globular clusters are all orbiting around something else means the sun is not near the center of the galaxy. Instead, it's someplace about 8 kiloparsecs away, which it isn't. It's further than that, but still. The main conclusion is that the sun is not the center of the galaxy. Remember, I promised you I wouldn't use the term parsec very much, but a parsec is about 3 light years. Apparently I'm wrong. Oh no, it's a kiloparsec. So that's 8,000 parsecs, which is about 26,000 light years. So that would be where the real center of the Milky Way is. Now that there are these two competing points of views, we've got to deal with all of these faint objects, all these Messier objects, or distant, dim, nebular objects, some of which aren't nebulas at all. And then you're grappling with the real question. How big is the universe? Is there one universe, aka is there one universe which happens to be our galaxy, or is there more going on there in outer space? So these two different points of view clash with each other. There's one of the spiral nebulae, which happens to be a galaxy, a spiral galaxy. Shapley's point of view is that the galaxy is the entire universe. Spiral nebulae are clouds of gas inside of the galaxy / inside of the universe. The sun is not near the center of the universe, but rather is part of a cluster of stars about 50,000 light years away from the center of the universe. The universe itself is about 300,000 light years apart. Not right in that most of these nebular objects are not inside of this galaxy at all. Curtis says the spiral galaxies are galaxies like our own, these island universes, and also that the sun is near the center of our galaxies. The galaxy is only 30,000 light years across. Not right. The sun is not the center of the galaxy. So they both got it wrong in different ways. They didn't have high enough data to conclusively solve the debate, but they both got something right. Shapley got the thing right that we are not the center of this galaxy. Curtis got the thing right that some of these Messier objects, the spiral nebulae, are galaxies like our own, and they are far away from us. So Shapley showed the Milky Way is larger than was believed, and that the sun is offset from the center. What he got wrong is that he believed the Milky Way was so large that it could encompass all these spiral nebulae that we see. Curtis's main contribution was to argue that the data available was not of sufficient quality to conclude that the spiral nebulae were inside the Milky Way, which was definitely true. So there's one of the spiral nebulae. As a matter of fact, it's one of the closest ones to it. It's one of the galaxies that's going to collide with our galaxy first. Other galaxies will collide with our galaxy later. This is the Andromeda Galaxy. And the way to solve the mystery is using redshifting. And here's a person who, quote unquote, solved the mystery, by which I mean that an army of grad students working for him solved the mystery, but he gets the credit. So there's a photographic plate of what Andromeda looked like to them at the time. And he looked at a bunch of these different nebular objects using photographic plates, and he came up with the idea that they evolve into different shapes. This is not right. I mean, it is right in a sense, but he got it going the wrong direction. I'll teach you about what elliptical galaxies and spiral galaxies are by the end of this presentation. You definitely do not start out with a circular galaxy and then evolve into a spiral galaxy. Rather, spiral galaxies collide, and as more and more spiral galaxies collide, coming from random directions, you get more and more and more of an elliptical shape. So this whole slide is wrong, but interesting from an historical perspective. And here's a bunch of modern pictures of what these look like. You've got elliptical galaxies over to the left and a bunch of spiral galaxies over to the right. The barred spirals, incidentally, indicates that the galaxy recently had what is, for lack of a better expression, a meal. When the central black hole consumes something that is extremely massive, gravitational effects from that destruction create short-lived bars that extend on either side of the black hole. And these bars dissipate over the course of several 100 million years, but they're present for a while. So elliptical, our Milky Way happens to be a barred spiral because Sagittarius A, our central black hole, has recently consumed something supermassive. We don't know what it is, but we know it did. And furthermore, we can see the intense radiation clouds above and below our galaxy from the galaxy eating something and then throwing out energy along its north and south poles as it does so. Remember that accretion disks create jets on either side, and so do black holes when they consume things. Here is a picture of what the Milky Way looks like in infrared from back when we used to have working infrared telescopes. And from that point of view, the central bulge and most of the spiral arms are much, much, much more visible. Remember, you've got to be on the side of the sun where you can actually see that. So that's summertime in the northern hemisphere, wintertime in the southern hemisphere. And here's what we think the Milky Way would look like from above. So it's a barred spiral. We are supposedly on the Orion arm. Excuse me, we're supposedly on the Sagittarius arm. I apologize. There is no Orion arm. I was misreading this. And really, much of this is a guess. If you ask a truthful astronomer how many arms the Milky Way has, they will probably say that we don't know for sure, but probably about 3 major ones. And that's because it's really, really, really hard to see the other side of the Milky Way. There's just too much stuff in the way. So we are on the Orion spur off of the Sagittarius arm, because the arms have little things that stick off on either side. And then here's an idea about how spiral arms form. Probably doesn't only happen this way. You've got a couple of masses of gas. And then they have some angular momentum relative to each other. They're set spinning because they're hit a little bit off center by some kind of shock wave. Think of a Coke can. If you hit it a little bit off center, it starts to rotate. And same thing is true of masses of gas. And just think about all the shock waves that are associated with this universe. Stuff happens one place, the shock waves propagate out, and that gives things angular momentum. It's like standing across the room and blowing on a Coke can with enough force to make it start to spin. As time, these clouds of gas, start to spin up and become thinner and thinner and thinner, and that's how you get spiral arms. It helps even more if there's a supermassive black hole in the center of this, although it's not completely required. We've found spiral galaxies without supermassive black holes. The give for them is that they don't have the big central bulge. So here's a pretty picture of an elliptical galaxy, which is one of the 2 main types we're going to study. And here's a pretty picture of a spiral galaxy, seen face on. Notice, not very many blue stars. Elliptical galaxies are much older. So all the blue stars have burnt out and turned into neutron stars or black holes, or if they've ejected enough mass, possibly even into white dwarfs. Every once in a while, a hot blue star will die in such a way that it sloughs off so much of its mass that it doesn't have enough mass left to make a neutron star, and it will just quietly turn into a white dwarf the same way our star will. But spiral galaxies have amazing amounts of star birth, and the star birth is mostly associated with the spiral arms itself. So one of the ways you can tell that you're looking at a spiral galaxy is that when you analyze the light coming from it, a goodly portion of the light is blue. And spiral galaxies look different in all kinds of different ways because we see them from all kinds of different angles. Here's a spiral galaxy face on, so we can see all the arms associated with it. But in reality, when we look out into space, we see spiral galaxies anything from completely edge on, in which case we've got all that dust obscuring our view of them. We can't really tell how many arms they have or a lot of details about them, or completely face on, which is ideal from the point of view of studying them. There's a blow up of spiral galaxy edge on, and get spiral galaxy a little bit off edge on. There is a third type of galaxy, which is called irregular galaxies. Irregular galaxies are basically what you get when 2 other galaxies collide. So let me show you the formation of an irregular galaxy. Exactly like what will happen to the Milky Way and Andromeda. So here's the Milky Way. Here's Andromeda, which is bigger by about a factor of 2. They're both headed towards each other. And in about 5 billion years, they will hit. And when that happens, you'll just get a big old mess. And that's an irregular galaxy. And this irregular galaxy will be called, well, it won't be called this because we'll almost certainly be extinct. But what astrophysicists are currently calling it is Milkdromeda, which I cannot say this enough. Astronomers, not good at naming things. So that's where irregular galaxies come from. It's pretty much from recent galactic collisions. So the difference between spiral galaxies and elliptical galaxies, which again are the two main types. You only see irregular galaxies shortly after collisions in between galaxies. Eventually, they settle down into being elliptical galaxies. Difference number one is orbital path of stars. Inside elliptical galaxies, stars orbit in random directions. So you get a big old circular bulge where every star could be orbiting around any possible direction. In spiral galaxies, stars are more or less in a flat plane and they orbit around in a circular pattern, much like a record does. With the exception of if there is a central black hole, there's a bunch of reddish stars around the central black hole, and those stars can have any orientation in their orbit exactly the same way an irregular galaxy can. And that's because that black hole, that supermassive black hole, has been holding on to them for a long time. So we basically have a tiny little irregular galaxy in the middle of many spiral galaxies. And that tiny little irregular galaxy is a result of the supermassive black hole that's just been attracting stars from wherever it can get them and holding on to them for a real long time, much longer than the existence of the spiral galaxy itself. Another difference is the preponderance of gas and dust in the stars. Spiral galaxies have lots of dust, and the gases come in many temperatures, including gas that is cold enough to form giant molecular clouds. In elliptical galaxies, there is very little dust, and it is super hot. Either there was not a lot of dust in the galaxies that collided to make the elliptical galaxy in the first place, or else the elliptical galaxy is so hot that the dust has largely been blown out into intergalactic space. And finally, the color is a big difference. Spiral galaxies, very blue, lots of starbursts. Elliptical galaxies, very red, and a lot of the stars that are present in it are turning into red giants, which makes them even redder. So elliptical galaxies have a young stellar population. Spiral galaxies have a young stellar population. Elliptical galaxies have a very old stellar population. All of the blue stars are dead, and because elliptical galaxies are so hot, because they're a result of collisions between different galaxies that have had time to settle out, the irregular galaxy stage is long past. The gas inside of them is way too hot for anything new to form. So there's big differences in between spiral galaxies and elliptical galaxies. And again, elliptical galaxies are basically formed by many different galaxies colliding. That's why they're spherical, because there's no preferential orientation to the stars in them. Galaxies collide coming from any plane that they wish to collide in. And that's why they're old and hot and they don't have any more starburst. When galaxies initially collide, when they are in the irregular galaxy stage, there was a huge burst of starburst. Like a bunch of new stars are created. But that starburst period also shocks the gas in the galaxy by so much that it's pretty much the last gasp of the galaxies that have just collided. So a bunch of new stars are born, but after that, very, very, very few to none will be created. And we also have the little minor galaxies that are around us. Here is the Large Magellanic Cloud. The Large and the Small Magellanic Cloud are pretty much only visible from the southern hemisphere. They look like the Milky Way. They're just a slightly brighter portion of the night sky. You need a telescope that can keep them fixed in its field of view and a CCD connected to it to really discern what their structure is. But I imagine it's very pretty. Remember, thanks to redshifting, we can tell exactly how fast something is coming towards or away from us. But if we want to know how fast it's moving from a side-to-side perspective relative to us, we have to wait and watch it for long enough to determine that. Because the large and small Magellanic Clouds are pretty far away, we haven't watched them for long enough. Consequently, we don't know their velocity well enough to be 100% sure that they're in orbit around our galaxy. There is still a chance that they are just passing by. So that is how much astronomers know about the direction of motion of objects. In the same kind of way that we don't know if one of our nearest star systems, Alpha Centauri, Beta Centauri, and Proxima Centauri, we don't know for sure that Proxima Centauri is actually part of that star system. It might just be passing by. The main way that we find out how far away galaxies are is a type 1a supernova. So white dwarf gathers enough mass, it explodes. All type 1a supernovas are supposed to be equally bright. If they are all equally bright, as soon as we observe them, we know exactly how far away it is. But another way is through variable stars. Here's where I'm going to risk to YouTube, but I don't think this one will be copyrighted. So there's a bunch of different variable stars, and they're all out of balance in terms of how much energy is coming out of the middle and how much gravity is pulling towards the middle. Consequently, they swell in size and then shrink in size, swell in size and shrink in size. And we think that according to the class of these stars, they pretty much all have similar characteristics. And so when we see stars that are brightening and dimming and brightening and dimming and brightening and dimming, we think that they're all similar stars. And if they are all similar stars, then we can look for these guys, assume that they all have basically the same properties, and then use that to figure out how far away a galaxy is. So that's another way. But a type 1a supernova is what we really, really, really want in order to do this determination. Regular galaxies, also bluish. Oh my. Hold on. My apologies. I elected to hit pause after showing you that video. So regular galaxies, also bluish. When two galaxies collide, you get a bunch of new stars being created. But then that's it. The gas colliding becomes too hot to really have any kind of new star formation after that. And there's what we think the Milky Way currently looks like. 100,000 light years across, the sun's pretty far out. There's a central bulge that's held there by a big old massive black hole that's been collecting stars for a while. Consequently, the stars orbit in more or less a spherical fashion. But the rest of the galaxy is pretty much a thin disk because it's made out of clumps of gas that have been moving slowly towards the middle and winding up into these flat spiral arms or the flat structure for quite a while. And there's a globular cluster surrounding the galaxy. If you enlarged a pancake in a DVD to the size of a galaxy, a DVD would more closely resemble the thickness of a Milky Way. Now, this presupposes that any of y'all remember what a DVD is, so ask your parents. Here is what we think the Milky Way looks like. As I said, probably three major spiral arms, maybe not. The entire side of the galaxy that is on the other side of us from the center is a complete guess. We really don't have good data on that at all. We can see that there's at least one spiral arm out there for sure, but that's about it. And spiral arms are sites of recent star formation, thus they must have giant molecular clouds and a bunch of dust. And because they are recently star forming regions, you're going to see a bunch of bright blue stars. And here is how a spiral galaxy forms. As time passes, it winds up and up and up. The spiral becomes tighter. And if you're wondering why it's flat, I will return you to all the analogies as to why the solar system is flat. You take pizza dough, you spin it in the air, and it becomes flat. That's why it's flat. There you go. Without going into the physics of it, that is how it works. All right, I don't think anybody's actually here, so I'm going to pause for a moment. Nope, nobody's here. And we're back. Spiral arms. The stars that are currently in spiral arms were not always there. You can think of spiral arms as being a kind of an energy wave or a density wave that goes throughout the galaxy. It behaves much like cars in a traffic jam. So which car is in the traffic jam changes as time passes, but the traffic jam itself remains. In this analogy, the cars would be stars and the traffic jam would be the spiral arm. So back to the anatomy of the Milky Way. We've got the older stars in the middle, stars that have been captured by the central black hole for kind of a while ago, which orbit around it because it's just been attracting stars from every which direction, and so they all have red. And then towards the outside, you've got this thin disk that was built by clouds of gas being attracted and acquiring some angular momentum. Remember, spinning pizza dough becomes flat. And then around that, you've got the globular clusters, the super ancient, mysterious spherical objects that have been around more or less since the first moments that stars could form. And we don't really know a lot about them, but the bigger a galaxy is, the more it can hold, and the Milky Way is about 75, give or take. The further away you get from the middle of the galaxy, the older the stars are. The further away you get from the center of the spiral, the older the stars are. This is because new stars are born from the spiral arms, and they travel pretty much in a flat plane. And then after that, the stars kind of drift away from the center of the galaxy. They actually oscillate up and down in the center of the galaxy. There's this whole theory of extinction that as Sol star oscillates up and down in its orbit in its spiral arm, mass extinctions happen as we get towards the edge of the protective layer of the spiral, and then we go back into the spiral, and then next time we come out, on the other side, there's a big extinction wave. I don't personally put any stock in it, but some people do. Chemical evolution in this Milky Way. Depending on the size of the stars you are, you either jet off a planetary nebula, like our star will do, and that's almost all. No real new interesting happening to build new stuff. The stars made plenty of carbon, but that carbon is locked into a white dwarf that's left behind. On the other hand, you can have a supernova, the ones that come from a really huge star, and they go bang in a way that spreads not only the heavy elements they've made all over the place, but they also create tons and tons and tons of neutrons that fly around, glom onto elements, and then a sizable number of them will turn into protons, which gives you new elements. We talked about all this in high and low mass stars. So when we observe the older stars in the halo, which surrounds the galaxy, the bulge in the center of the galaxy that the central black hole is attracted, and the outer part of the disk, there's a lot fewer heavy elements in the spectrum of the stars than there is in the younger stars towards the center of the disk. Now, here's a weird thing about the orbital motion of the solar system. Planets in our solar system follow Kepler's laws for orbits. Mercury orbits faster than Venus, orbits faster than Earth, so on and so forth. For the stars in the galaxy, all of the stars orbit at roughly the same speed. This can only happen if something called dark matter exists. And I'm going to talk more about dark matter in Unit 14, so it's a ways off. But wait for Unit 14 for an explanation of how these truly weird orbits can occur. And the implication is that there is a significant amount of mass in every galaxy out in a gigantic halo surrounding it that is much, much, much bigger than the star part of the galaxy. And there's the orbital speed of stars and spiral galaxies as measured experimentally. And that's what the orbital speed should be if they followed proper Keplerian motion. So there's an orbit in the disk, there's orbits in the halo. They are slightly different. More about both of these when we finally get to dark energy. And there's where the dark matter. And there's where the dark matter halo would be. Only this is really, really, really not to scale. The dark matter halo would actually have to be much bigger than this. So we consider dark matter to be part of the galaxy, and in order to explain the orbits in the visible part of the galaxy, in the stars, the dark matter would have to comprise about 90 to 95% of the total mass associated with the galaxy. So most of the galaxy is stuff that we can't see. There's two current hypotheses, machos and WIMPs. Machos would be objects that we can't see, which are nonetheless big. So like our galaxy is holding on to a lot of black holes, neutron stars, white dwarfs that have cooled off and become black dwarfs. Nobody takes this hypothesis very seriously. What we really think it is, or what most astronomers think it is that it's some kind of particle we haven't detected yet. The particle would have a lot of mass, but it would stream through normal matter, like a neutrino does. But neutrinos are very light. This thing would have to be very heavy. And we've never been able to detect them, but nonetheless, we think that it probably has to be that. So if there is a supermassive black hole in the center of a galaxy, you get all these random orbits around it that make an overall sphere. Some supermassive black holes are just swallowing a lot of matter. When they are, you see a bunch of jets, and the spiral galaxy quickly becomes a barred spiral galaxy. And then eventually the distortion ends up resolved and it turns back into a normal unbarred spiral galaxy. Our galaxy recently had such a meal, and we can see both that it has a bar and the big old radiation explosion from the top and the bottom of the galaxy stretching out into the intergalactic space. There's an artist's conception of what this would look like. Now, it's going to be a lot more about quasars later, but basically, quasars are galaxies that we can see that are very far away. Because they're very far away, they're very old. Because they're very old, they existed at a time when the universe was much denser. Because the universe was much denser, it was much easier for those central supermassive black holes to have a meal, and to have a bigger meal. They were often encountering objects that they could rip apart, consume, make jets, and become even heavier. And so the jets that they create were so powerful that even though these things are really, 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 really far away, we can still see the jets if they happen to be pointed directly towards us. And a sizable number of them are because apparently there was a lot of galaxies that were doing this back in the day. Here's a couple quasars imaged by the Hubble Space Telescope. One of these is, one quasar. One of them is a star in the middle of our galaxy. The other is a quasar, 9 billion light years away. There's no easy way to tell where this super nearby star is and where the quasar is unless you analyze the red shifting and the blue shifting associated with it, because they're both about equally bright. When a galaxy has a meal, like our galaxy just has, jets come out of the top and the bottom, and we see them. And we see this explosion into intergalactic space. We can see this with the Milky Way. Because again, it's pretty easy to see above and below the galaxy. It's just hard to see things within the galaxy. Here's another actual picture of a distant galaxy that has had a meal recently, and you can see the jets coming out of it. And here is a measure of quasars as a result of time. Notice that there used to be a lot of them. And then as the galaxy expanded, there was less and less material available for black holes to consume. And so quasars became far less common until the point at which we're at now, and we basically don't see any. Here is what we're at locally. So everything that's a blue dot is a small, very minor galaxy. The three things in yellow are major galaxies. We've got the Milky Way, we've got Andromeda. Andromeda is going to hit the Milky Way first, and we'll briefly have an irregular galaxy as the two of them collide, and then it will slowly settle out into being an elliptical galaxy. We will also eventually have Triangulum hit Milkdromeda by that point, and presumably almost every other minor galaxy, if not every minor galaxy, will eventually get pulled in, and we will be a gigantic elliptical galaxy instead of some spiral galaxies and a bunch of minor galaxies. Here's Andromeda. It's coming right for us. Here's a Triangulum. It's not coming right for us yet, but once Milkdromeda exists, we'll have enough gravity to definitely pull it in and consume it. The Large Magellanic Cloud is in orbit around us. It's one of the dwarf galaxies. We can't actually tell if it's in orbit or not because we haven't watched it for long enough to know if it is moving past us or in orbit around us. There's what the large and small Magellanic Clouds look like from the southern hemisphere. Again, you can't see them from the northern hemisphere at all. And there's plenty of evidence that the Milky Way has consumed minor galaxies before. We can see these streams of stars above and below us when the Milky Way's basically taken a small galaxy that's come a bit too close and ripped it to pieces. This impact is not big enough to turn the Milky Way into an elliptical galaxy at all. It's just a normal huge spiral galaxy that's ripped apart a tiny little galaxy. And eventually we'll absorb it into our structure. All galaxies exist in clusters, which may contain up to 1,000 galaxies. So what I showed you before is just our local group. We're part of a larger group beyond that. The bullet cluster, I'm going to talk about the bullet cluster in Unit 14. But basically no, I'm not going to talk about it now. There's not enough background. So astronomers can model the observed distribution of galaxy clusters using computer simulations. Each one of the bright knots in the image represents a supercluster containing about 10,000 galaxies. And the bright bits are called filaments, and the dark bits are called voids. And the voids basically don't have galaxies in them. And now we have reached the point at which it's time to look at some simulations. So let's do that. I'm sorry, I don't know any better way to do this than to launch a VLC, share it, and then come back. So we start out, we assume that galaxies are more or less equally distributed, and then slowly they clump up like that. Let me show that to you again. So we get filaments and we get voids. This is what's happening on a very local scale. If you look at this from a larger perspective, oh no, do not close the PowerPoint. Then you get something that looks, at least according to our simulations, a lot more like this. So this is how filaments and voids both form. Gravity basically makes things clump up. Let's look at this one more time. Again, this is a computer simulation. We don't know for sure, but it is our best guess that filaments and voids form this way. And then, since we've been talking about it so much, here is, sorry, back to share screen. Here's a computer simulation as to what a spiral galaxy looks like if you were to rotate all the way around it. This one does have a central black hole. And this is a computer simulation of two galaxies colliding. So this is how you get an irregular galaxy. They fly through each other briefly, but they both have sufficient gravity that almost all the material gets pulled back towards a central spot. The orbits of the stars get pretty much randomized, and now instead of being a spiral, they become something that is a much more random distribution. One more picture of the same kind of thing, if I can slow it down adequately. Play back to slow as possible. So here's two spiral galaxies, much like the Milky Way and Andromeda. And that's what you get after they collide. The simulation runs way too fast. Keep in mind I've got it running on slow as possible. So briefly irregular, and then eventually elliptical. Back to the presentation. So there's the local group. Notice there's three bright dots in it. That's Andromeda, the Milky Way, and Triangulum. We are loosely associated with the filament called the Virgo cluster, so named because it's in the direction of the constellation Virgo. And I've already shown you how large sections of galaxies form. Here's our local group again. This is what it will look like as Andromeda comes closer and closer and closer to our night sky. Of course, this is happening 5 billion years from now, so the Earth is done for. This will be around when the sun enters a red giant stage. So this is what it would look like if our planet were still here, where you have the clear spiral galaxy getting closer and closer and closer, and then everything becomes a jumbled mess. So 1, 2, 3, both galaxies are still more or less spiral arms. 4, 5, 6 is a regular stage. 7 and 8 is when it's resolving into being more or less an elliptical galaxy. And then, how many galaxies are there? Let's go back to the board. So I showed you a picture of an image that the Hubble galaxy took. And what I want to emphasize before I go back to the picture is that the field of view of the Hubble, when they took that picture, is the same field of view as what would be blocked by 1 grain of sand held at arm's length. So let's go back and try to make a count of how many galaxies we see in that picture, and then imagine how many grains of sand it would take to completely surround your eye in all directions. The answer is a lot of grains of sand. And that one grain of sand blocks a whole lot of galaxies. One of the objects in that picture is a star, just happened to be in the field of view. Every other object in that picture is a galaxy. So count up every galaxy you see, realize that that number of galaxies is the number of galaxies that would be blocked by one grain of sand, and then you can imagine how many galaxies there are in the visible universe. And keep in mind, the visible universe is a small portion of our total universe. We don't know exactly how small a portion, but it's a portion only. Here's a static representation of filaments and voids being formed. And here's our plan of the day. Neptune can be seen through a normal telescope, and if you have excellent eyes, you can theoretically see it with your naked vision. Theoretically. Neptune has a moon, Triton, that is basically identical to Pluto, and Triton is in a backwards orbit around Neptune. That means that Triton orbits in a direction that is opposite the direction that Neptune's spinning. Anytime you have a captured object that's orbiting in a direction that's opposite to the planet's spin, that orbit is unstable. Triton's eventually going to hit Neptune. That's just inevitable. Also, Triton is basically as big as Pluto, and it's another part of the reason why Pluto was put on the chopping block. Because if a moon of a planet is basically the same thing as Pluto, where are you going to draw the line? Pluto can't be a planet because Triton is just a moon, and it's basically identical to Pluto. The most interesting thing about Neptune for me is how it was found. And so we're going to end with a video exploring that. And I'm only going to show you a small portion of the video, but nonetheless, it's going to be extremely interesting. So enjoy it, and recordings will not include audio. I don't want that. So maybe I need to be unmuted for YouTube to work. Here we go.
I'm going to talk a little bit about some of the things that Eugene talked about Pluto, about the discoveries in this region of the Kuiper Belt that I'll show to you. And I'm going to show you how those have led us onto our new quest, which is to find the real ninth planet in the outer part of the solar system. We call it Planet 9 because we're not very creative. But when we actually find it, it'll get a real name. And I think I'm going to try to convince you today that it's really out there and that we really will find it. The story of another planet in the solar system beyond the one that we know of actually starts in something like 1790. 1790, Uranus had just been discovered, and astronomers were interested in whether or not Uranus was a planet. Uranus was discovered by chance, but by chance of a very careful astronomer who was charting positions of things in the sky, saw something that looked a little bit unusual, it looked a little bit fuzzy, and he went back and looked the next day, realized it had moved. And that is and remains the key signature of something that's part of our solar system. It's moving compared to all the background stars. And this was William Herschel who made this discovery. And I sometimes try to step back to that moment in history because this is, thinking about finding new planets is pretty exciting. But imagine this first planet ever discovered in history. All the planets up to that point, were all the way out to Saturn, could be seen with the naked eye. Everybody knew about these planets. Uranus was the first one that was discovered by a telescope. I I've never been able to find anything written down about what a sort of psychic shock that was to humanity to realize that the solar system was bigger than they possibly thought. There's a new planet out there. They didn't know for sure it was a planet at the time of discovery. They knew it was something in the solar system moving. And one of the things they thought it might be is a comet. They knew about these things called comets. They knew they were on these very elliptical orbits that went out quite far away, came back in. And so the question that everybody had at the time of the discovery of Uranus is, what kind of orbit does it have? Does it go in a circle around the sun, like all the planets do, an ellipse really, but we'll call it a circle, or is it on a very elliptical orbit? The only way to figure out what kind of orbit it has is to sit and watch it year after year after year and see it as it goes around the sun. Uranus takes about 80 years to go around the sun. 80 years is a long time to wait. So, in about 1820, an astronomer named Alexis Bouvard in Paris decided that he didn't want to wait 80 years to figure out the orbit. He was going to go back in time and see if he could find it. So what he did is he would go back a couple of years and look at other astronomers' data where they had drawn where all the stars were, and he realized, hey, this person drew a star there, but there's not a star there anymore. That could have been Uranus. And he says, okay, if that's it, I'm going to now go back another couple of years. There's a star where there's not supposed to be one. And he put it there and went back a couple of years. And he went back all the way to, if I'm going to show you this table just because you can't read it, he went all the way back to that very first thing on the top of that plot there is 1690 was the first time anyone had actually seen Uranus was 100 years before its discovery. And he has data now from 1690 all the way up to 1819. He went through this math, and I'm going to now go through line by line. I don't even understand what all this is. Eugene probably does. Do you know what all this stuff is? He does. He's nodding yes. But the important thing here is that he has all the positions of Uranus from 1690 all the way up to 1819, and he proved in somewhere up here, he says in French, that it's on a circular orbit. He proves that it's really a planet. This is his big result. He also shows it's not quite where it's supposed to be all the time. The little pluses and minuses that you see here in the second column are how far away from where it's supposed to be that it really is, and it's kind of deviating here and there. And he does what any good theoretical astronomer does when presented with data that doesn't make sense. He decided that the people who were doing the observations probably were bad, and you shouldn't trust them. He actually says this here. It's difficult. I don't know. If you read in French, you can see it where he says it up here. He does mention the possibility, however, that there might be something else beyond Uranus perturbing its orbit. He then actually gave his observations, gave his data to an astronomer also at Paris, in Paris, Leverrier, and he said, you should try to figure this out. There might actually be something out there. Leverrier worked on it for a while and realized that he could explain these data very precisely with a planet beyond Uranus. Leverrier went to basically the French Academy of Science and presented his results, and they were all very excited, and they clapped in their very excited ways. Yay, nice job, Leverrier. And he was very excited. He wanted them to go look for it because he could tell you exactly where it was, and it did not occur to them, I think, that you could use math to discover a planet. They didn't really think that this was reality. They really thought that this was a really beautiful mathematical demonstration that you could make the numbers work out, which is not the same as thinking that you can use physics and math to predict things. And he's like, no, there's really a planet. Go look, it's right there. And then, yeah. So nobody in France would look for this planet. He finally contacted the Berlin Observatory, and they opened up their telescope, pointed to exactly where he said it was, and they found it in the first night of his observations. There's Neptune was right there. And to me, these two moments, Uranus as the discovery of the first discovery of a planet, which just changes the way that people must have thought about the solar system. But Neptune, the first really good demonstration that math, this newfangled math and physics stuff, actually is describing reality. It's not just a cute trick to make calculations. you can actually find things you didn't know that were there based on this math and physics. And I think those two things were an incredibly powerful realization. And this is in 1845. There's an obvious thing to do. As soon as you have discovered a planet using math and physics, the obvious thing to do is to look for the next planet. So Uranus was discovered by accident, by careful observations. Neptune was discovered by math and physics. A slew of astronomers immediately started wondering, now it's obvious, there must be something else out there too that we haven't found. Let's go find it. So they started analyzing the orbit reanalyzing the orbit of Uranus, looking at the orbit of Neptune as observations were coming in, and trying to see if there was something else out there. The most famous of these predictions of another planet beyond Neptune, there was a series of people working on it, but the most famous one by far was from Percival Lowell. Percival Lowell predicted, he had a series of predictions, but the one that really hit home was the one that he called, I think he's the one who originally called it Planet X. This large planet beyond the orbit of Neptune that's perturbing the orbits of Uranus and Neptune. And he predicted exactly where he thought it was supposed to be using the same methods that Leverrier did to find Neptune. And he sent some astronomers up to Mount Wilson, which is in Southern California. Actually, it's literally my backyard. You can see the mount where he is. And they took a picture of the sky, and it looked something like this. And do you see the night planet there? No? Okay. He didn't see it either. The astronomers didn't see it. But they were looking for something big. They were looking for this sort of Jupiter-ish sized object that was tugging on Uranus and Neptune. And a Jupiter-sized object, it would be obvious. It would be like this big in the frame here, and you would take a picture and you just know. They didn't see anything here, so they went back. He went back to the drawing board, kept on doing calculations. He died before anything was ever found out in that region of space, but not before he founded the Lowell Observatory in Flagstaff and set them out on the quest for Planet X. In his quest for Planet X, in their quest for Planet X, they built a special telescope to look for it. They hired Clyde Tombaugh off of a farm in Illinois, and Clyde Tombaugh took a few pictures that looked kind of like this, and realized that he was smart enough to know that he didn't know what a planet looked like. And he was smart enough to remember all these things that we knew about planets, which is the real way you identify a planet is you don't look for that big disk in the sky, you look for something that moves. So he took a picture one night, and then he would take another picture the second night and watch it move. Did you guys see it move? Sure you did. Okay, let's try this again. Here's the first night. There's the second night. How many people think they see it? Okay, we'll see. Okay, we'll try first night, second night. I don't know why, but if you repeat things 4 times, it's a function of physiology. The 4th time, everybody sees it. So let's try it. The first night and the second night. These are actually Clyde Tombaugh's discovery images of Pluto. And Pluto was very close to the position that Percival Lowell had predicted Planet X should be. And so prediction was made, discovery was made, New York Times headline on the day of the announcement of discovery, 9th planet discovered, first found in 84 years. Neptune was the one, lies far beyond Neptune, so far so good. Sighted January 21st. Search begun by Percival Lowell. Good. Special photo telescope. Good. Makes thorough check. Good. The sphere possibly larger than Jupiter. Meets predictions. Those are the big problems. Those are actually, that little phrase right there contains the entire story of why Pluto was a planet and is no longer a planet. Possibly larger than Jupiter. I'll show you in a minute.
All right, that's as much as I'm going to show you that one. Everybody have a great weekend/week, depending on when you're watching these. As soon as NBC translate this file, I'm going to try to upload it to YouTube. I'll send a class email if it works. Bye.